Alright, hello everyone. So today, like what I said in the last video, we're going to solve a problem involving our non-ideal op-amp, which we analyzed quite in detail in the last video. Alright, so before starting on the problem, I guess I'd like to clarify some things. Um, okay, so the first one, where did I write it? So I see, okay, so the op-amp model I wrote here is IC741. I just forgot to mention IC here is short for integrated circuit. Okay, so integrated circuit, and op-amps in general are integrated circuits. So this is integrated circuit. So that's just that. Um, and the other one, I might have mentioned this. I just didn't remember. The reason why I didn't include pins 1 and 5 here, okay, in the circuit diagram for the op amp, is because, as I said before, these are just to balance a small error when the output voltage is supposed to be 0. They're not really something critical, and certainly do not affect any of our calculations. All right, so with all that out of the way, let's jump right into the problem. And well, this problem, I need to give due credit. So this is from a book called Fundamentals of Electric Circuits, written by Charles Alexander and Matthew Sadiku. So let me first draw this circuit. So what I have here is, let's see, so you have cell here, okay, which has a voltage of EMF of Vs. Let's see. Then you have a okay, wait. I'll draw the resistor like that. Okay. So you have this resistor. Um, then you have the op amp here. You have the op amp here. I'll try to make it as large as possible. All right. Then you have this here. In the bottom is your ground. We have extended to here. This is the other one. Yeah, here you have the ground. Okay, it's not a cell, this is the ground. um, and also here's your output terminal, and you have 20 ohms linked over here. Oops, again. Again. Oops. All right, so this meets here. All right, so and this is 10 kilo ohm, 10 kilo ohm. This is 20 kilo ohm. Let's see. Yeah, and well, this is definitely the ground. So the output here is obviously, this is just labeled as V naught, V naught, as we have been doing. So the as we know, the output voltage here is V naught. And I'll pause for a second because a cat is really. Alright, sorry about that. There was a stray outside. Stray cat. Okay, so where was I? Did I forget to label anything? No, that's done, that's done, that's done. Okay, so yeah, this is my problem, and well, we are not done. The problem says that my open loop voltage gain, so it's A, our capital A is our open loop voltage gain is, let's see here, so it's um, this is equal to 2 times 10 to the 5. All right, as I said in the last video, this gain is pretty large for op amps. Then you have your input resistance, okay, the op amp's input resistance, which is R sub I. This is equal to 2 mega ohms. 2 mega ohms. Your output resistance, which is pretty small compared to the other ones, as I said before, so that is your output resistance. I'll write it here. I don't know why I need to write all of these such a congested manner. So this is 50 ohms. This is 50 ohms. All right. Um, anything else left? I don't think so. 50 ohms. Uh, okay. So what we need to determine is my the closed loop voltage gain. Okay, or in other words, um, I need to find, and I'll explain why this is called the closed loop voltage gain a bit later. Um, First, we'll just try to find this ratio. So we need to find this closed loop voltage gain, this ratio. Okay, so we need to find this ratio, and we also need to find um, okay, so we also need to find this one. Let's see. So we need to find this current when Vs equals 2. Okay, so we need to find this current when Vs equals 2 volts. Correct. So when Vs equals 2 volts. So these are what we need to find. This is really our, this is our main problem, and if we just solve this would become pretty easy. But anyways, so and well, I should label the terminals of the op amp. They did label them here. So this is a minus, and this is a plus. But suppose say if for some reason some poorly written question doesn't have them labeled, you should still assume that the upper one is your inverting terminal. Okay, your inverting input, and the lower one is your non-inverting one. Anyways, so. Uh, so what do we do? Basically, what do we do now? Well, uh, we actually refer to what we did in the last video. In the last video, if you see here, where is it? Okay, so I I drew this equivalent circuit. Okay, at at least at the input terminals, from the perspective of the input terminals and the output terminal, I drew this equivalent circuit. Okay, of the op amp. Um, for ignore all these dots and the triangle silhouette. So this is what we are just going to plug in. Okay, instead of the op amp, in place of the op amp. Okay, so as we know, equivalent circuits, we can just plug them in for what's originally there, right? So what we have here, it really would have been better to draw this next to this one. Okay, I guess there's no space for that. Anyways, so anyways, let's see what's here. So at uh, between the input terminals, you have your input resistance, and Vd is the order of Vd. We know it's from V1 to V2. It's from the negative to the positive. That's clear. And from this terminal, you have your output resistance. You have this VCVS, and it's connected to the ground. Okay, it's connected to the ground here. In this circuit, this is the ground. So the ground of that is basically this one. So we need to connect that all the way here. Okay, so let's try to do that. Let's try to redraw this circuit. um, I'll, I'll I'll choose purple for this. So what we have, most of the things obviously are the same. We just need to replace the op amp. So this is Vs, this is Vs. Okay, and let's see, we have, I think it would be, I'm sorry for wasting so much time, but I think it would be better to keep a bit more space. I don't know why I need to keep things so congested. So this is Vs. I'll do this quick. This is your negative one. This is your ground. All right. Okay. So you have your 10 kilo ohms. Okay. You have a 10 kilo ohms here. Okay. This is connected to. Okay. So this is important, and I'll draw this terminal too, all the way up to here. Okay. So here, okay, so I drew these two terminals, and do all this. Okay, anyways, I'll ignore that. I'll fully ignore that. um, okay, so okay, so here you have your input resistance. So between these two, you have input resistance. By the way, if someone's if you guys cannot hear this, I don't know if this is coming into the audio, and you might be thinking, what am I ignoring? Am I ignoring some important thing? Actually, no. There's again another stray. This time a dog outside my house. So I was just wondering if all the strays just come close to me or what. So that's what I'm ignoring. But anyways, you can ignore what I'm saying about all that. Okay, so that as you can see, we just replaced uh, the op amp. Okay, this is going to have two parts to it. Okay, these were my input terminals, right? These were my input terminals. All I did was, as we saw in this diagram, we just put the equivalent circuit from this end is just your input resistance, this large resistance connected to your two inputs, and that's all I did here. I just put that resistance between those two input terminals. Okay, and same thing for the output terminal. What I'm going to do is replace it with this part. Okay, so it's your output resistance connected to a VCVS, this this A into V sub D, that cell, and then you have your earth. Then you have your earth, and the earth here is as they said, as they have already shown, that this is the earth. So we need to connect that all the way here. So let's try to do that. So our output, the one end is here. This is connected to my resistance, your output resistance. Now this is connected to um, your VCVS, um, and this is connected to the ground. So as in the diagram, this is the ground. Okay, and the reason I connected it here is because the ground, you already have the ground in the circuit here. So and that obviously goes in here. All right, so I don't need to draw that twice. So anyway, so okay, so this is perfect. The only thing left here is connect the 20 kilo ohms from here all the way up to here. Okay, so let's see, here all the way up to here. I really should have drawn this a bit more to the, okay, so okay, I'll, I'll draw that. Okay, so let's just say this is a node. This is in fact a node. But anyways, so this is my circuit. Oh, wait a second, almost forgot to draw the resistance. Okay, so this is 20 kilo. Not such a good diagram now, but I hope you can overlook these things. And well, you have your input resistance. This is your input resistance. This is 2 mega ohms. This is 2 mega ohms. 2 um, 2 times 10 to the 6 ohms. Let's write it. Well, I should have done all of them like that. Actually, uh, nah, I think we can manage that. I think we can at least manage the prefixes in the calculations. That's fine. We have 2 mega ohms here. We have 50 ohms as the output resistance. So this is 50 ohms. This is 50 ohms. All right. This is V sub 0. This is V sub 0, and basically this is the same as the, this is the value of this node, this whole node. Okay, so that's V sub 0. Yeah, I'll write it there too, and I'll write it here too. So this is V sub 0. Okay, this is basically V sub 0. Okay, and this is A into VD. This is A into VD. But there's actually one interesting thing. You can already make simplification here. What is VD? Right? What is VD? Well, this is VD. This was your non inverting input. This was your non-inverting input, and VD is basically the difference. The difference between these two, right? So this is VD. This is VD. Okay. Now, if I the non-inverting input, sorry, yeah, this is the non-inverting input. Well, that's ground, so I don't need to label that. We know that it is 0. But if we want to, we could say that V sub 2 equals 0. Okay, 0 volts. All right, so that's done. The other one that we have left is V sub 1, which is your inverting input. Okay, and this one we'll just say that this is V sub 1. Okay, this is V sub 1. All right, so what is VD? It is V2 minus V1, but V2 is 0. So VD is, I'll write that down. This is important. So VD is, this is a good simplification. VD is 0 minus V1. Okay, or it's just negative V1. It's just negative V1. All right. This is going to be important, and I'll label some nodes here. So this is, let's say this is node 1, and oh yeah, obviously I forgot to say this, but I think you can see this already. The moment we replaced this op amp with these two equivalent circuits, this has just become your regular circuit with just one cell and one um, dependent source. So we just need to apply our regular circuit theorems and analysis methods, and this will be solved. So I think, okay, so let's just go about it. Let's just go about it. This is your node 1. Let's say this is your node 1. Let's say this is your node 2. Okay, this is your node 2. And let's try to do a nodal analysis. Okay, so let's what am I saying? Let's first apply KCL at node 1. Okay, let's see. First I'll label the currents just to make things a bit clearer. So at node 1, suppose say we have a current entering from here. Okay, we have a current entering from here. um, we have a current, let's say, exiting from here. Okay, exiting from here. All right, and we have make it enter or exit. Let's make it exit here. Let's make it exit. So we have a current um, exiting from here. All right, so the current entering must be equal to the current exiting, right? That's KCL. So at node 1, let's do it in this color. At node 1 we have this equation. So at node 1 we have, so the current entering, as you can see, it's the voltage difference. So here the voltage is Vs, because this is the ground, so this is Vs, right here. This is Vs. So Vs minus V1, this is V1, divided by 10 kilo ohms. Okay, so this is the current entering node 1. So Vs minus V1 divided by 10 kilo ohms, or 10 times 10 to the 3 ohms. I'll omit the ohms. Okay, okay, so this is going to be equal to the current exiting. So the current exiting here is V1 minus VO. Okay, VO, this is my voltage here, my potential here, divided by the resistance between. So this is 20 kilo ohms. So V1 minus VO. I'm sorry if I've ever said that this is V naught. This is not V naught, this is V sub O. Okay, for output, it's not naught. Alright, so divided by a resistance which is 20 kilo ohms, 20 times 10 to the 3, plus we have another current, this one, which is exiting here. That's a V1 minus V2, but V2 is 0. So V1 divided by our resistance, which is 2 mega ohms. V1 divided by our resistance, which is 2 mega ohms. Okay, so V1 divided by 2 times 10 to the 6, 2 times 10 to the 6. Alright, so we have our equation, but let's simplify it a bit. I think it would be good if we multiply both sides by 2 times 10 to the 6, right? If we do this, this is at least a common denominator to common multiple to all the denominators. If we do that, okay, we would be simplifying this. So if we multiply, I really don't know why that color stuck. So if you multiply both sides by 2 times 10 to the 6, so this is, let's see, 2000 by 10, that's 200, right? That's 200 Vs minus 200 V1, hope I'm getting this right. This is equal to, so 20, let's see, 2000 divided by 20, that's 100. Yeah, that's 100. So 100 V1 minus 100 V0. Okay, plus V1, okay, plus V1. All right, so this simplifies to, let's see, so we have, let's collect the terms. So we have Vs here. Do we have any other Vs's? No, we don't. So we have 200 Vs. This is going to be equal to, we have V1 here, 200 V1, and if we add that, so this is 100 V1. So we have 300. Actually, there is another v1 here, so 1 v1. So 301 v1, 301 v1, and minus 100 v naught, right? So minus 100 v naught, minus 100 v naught. There's no other v naughts. So this is my equation. This is what we get from the first node. This cannot be simplified any further yet. Okay, so we'll leave that as it is. We'll leave that as it is for now. Let's move on to node 2. Let's move on to node 2. So at node 2, okay, what we have is, okay, so we have this current entering. Okay, we have this current entering, and let's say we have this current exiting. So the current entering is obviously equal to the current exiting, right? So the current entering, we actually already wrote an expression for this. This is the same as this one, right? So this is the same as this one. So we'll just write that again. This is the current entering is V1 minus V naught divided by 20 times 10 to the power 3. Okay, so that's the current entering, and the current exiting is let's see, V naught minus A into VD, V sub D divided by 50. But before writing that, I'd actually like to do a simplification here. Well, first thing is, we know A is just a number, right? A is just, your gain, open loop voltage gain, which we know this is 2 times 10 to the 5. That's not an issue. We can just substitute that, and we also know what VD is. We also know what V sub D is. That's just equal to minus V sub 1. That's just equal to minus V sub 1. So I'll actually, first of all, let's just write the current as it is. So we have V naught, as we said, so V naught minus A sub VD, okay, and it's going to be divided by 50. But before writing that, I'll just simplify this one. Okay, so as we said, A is 2 times 10 to the 5. A is 2 times 10 to the 5, and VD is negative V1. VD is negative V1. Okay, and I can make these two positive. Negative negative becomes positive. So I'll make this positive. So that's a fair bit of simplification. Divided by resistance 50. All right. Let's simplify this. Let's multiply both sides by. Let's see. What do we need to multiply by? Okay, so 20 times 10 to the 3. Let's multiply by that. So what we have is V1 minus V naught on this side equals. Okay, so let's see. Let's doing these mentally is becoming a bit tiring. So 100 by 50, that's obviously 2. 2 times 200, that's 400. That's 400. That's 400. V naught plus 2 times 10 to the 5. 2 times 10 to the 5. V1. Okay, and if we simplify this now, before going any further, we obviously should look at what our goal is. Our goal is to find V naught divided by Vs, right? V sub s, and here we have an equation that has Vs, V1, and V naught. Okay, these three. We'd actually like only Vs and V naught, right? We would want to make V1 disappear. Okay, we would want to make that disappear, and here we do have an opportunity for that. We can, as you can see, there's only V1 and V naught here. We can fully express V1 in terms of V naught. And if we do that, we'll only have V, and if we do that and then substitute V1 here, we'll only have Vs and V naught here. And then you can find the ratio pretty easily. Okay, so that's what we're going to do. That's what we're going to do. We should express V1 in terms of V naught. Okay, so V1, if I do this pretty quick, this is going to be V1 is, the factor here is going to be, so 401. So you have 401 on the numerator, 401 on the numerator, and in the denominator you have, okay, so you have 1 minus 1 minus, so 1 minus 400 times 2 times 10 to the 5. So I'll write it as 8. 4 times 2 is 8 times 10 to the 7 times 10 to the 7. All right. So, and this is multiplied by V naught. So I'll just substitute that here. This is getting pretty awkward actually, this. And yeah, I really want you to see the awkwardness of all this, and then we can appreciate more the usefulness of the ideal op amp, okay, and how easy it makes our calculation lives. Before that, let's just endeavor to solve this accurately. So 200 vs, so we have 200 vs. We substitute this thing into our first equation. We have 200 vs equals, okay, so this into v naught substituted here, minus 100. So we have let's see, we have 301 into 401 divided by 1 minus 8 times 10 to the 7. Weird, very weird factor. Minus 100, and a lot of you might see, those of you who have done these estimations in school, where you can just consider this 300, consider this 400, and ignore the 1. Yes, those are pretty good estimations, but again, I'm not doing those now, just so that we can appreciate more the magnanimousness of the ideal op amp, okay. And that is I'm sorry, sorry for stuttering. The ideal op amp does makes these simplifications and a bit more than that, so we'll do that at that time. But we're almost done here. This very tedious calculation. So v naught by vs is just going to be 200 divided by all of this. I'm not going to try to write that. I'll just plug this into the calculator. So it's, and I don't think there's a point in showing you the whole thing, so I'll just pause for now. So I'm back. As you can see, I typed all this into the calculator painstakingly so, and what we got from this is, and I'll write it to more significant figures than it might have to be, but anyways, I just want to show you again in the next video just how great the ideal op amp is. So you have 4 nines and then a 698, okay, 4 nines and then a 698. So this is, and well, we could at least for now, I did said write this accurately, but also just as a simplification for the rest of this time, for the rest of the consideration, this is approximately -2. But anyways, this is our answer. So as we can see, so we are done with the calculation. We found this ratio that they told us. Also, we can easily find I. Okay, so I is basically this current. We have the formula for that, right? This is actually I. Okay, this is I. And it's not difficult, given we have Vs. Since we have Vs, we can easily find, from that ratio we can find V naught, and we can also find V1, right? Where is that? Where is V1? How can we find V1 here? Let's see. V1, yeah, okay, so we can find V1 from here, from V naught. We can find V naught from Vs, or we could just make some substitutions here. But anyways, this I is actually pretty easy to find, so I'm not going to go through that. What I'm more going to focus on is so as far as calculations go, we are actually done here. Okay, so if that was your goal, just see how to deal with non-ideal op amp calculation, you're actually, you have fulfilled your mission. So we are done with the calculation, but I'd just like to see what's exactly happening here. I explain some of the things, like why this is, the closed loop gain, etc. So please do stick around. So let's see what's the first thing on the agenda. Okay, so yeah, the first thing is obviously what I said before. Why is this called the closed loop gain? Why is this called the closed loop voltage gain? Okay, and to answer this, before answering this, I'd like you to consider what would happen if this wasn't, suppose if this wasn't this part right here, if this was open, or if this branch just wasn't there. Okay, so I'm just being lazy and just uh, causing an open circuit here. So anyway, so I'd like you to consider what would happen if this was an open circuit. So if this branch just wasn't there. um, Basically same thing here. This is going to be open. It's going to be open. All right. So and now what's going to happen? Now what's going to happen? Well, this current is 0, this current is 0, and so V naught is going to equal is going to exactly equal, because the voltage, there is no potential drop here, so V naught is going to equal A into V sub D, and V sub D being equal to minus V1 is it's still correct, even though this is open. It didn't, this did not affect this part, so this is still correct. So we actually have so for this open part, if we have this open circuit, I really wanted more space here. Unfortunately I'm not getting that, so I'll still try to do this here. So V naught is going to equal negative A into wait, no, not yeah, okay, so negative A into V1. No, that is correct. All right. The other thing is, so this is a closed, this is a loop, this is just a single loop, and there's no current flowing through here because this part is open, so there's no current here, so it's just an independent loop. Here Vs is you have Vs, which is providing the EMF to these two resistors in series, 10 kilo ohms and 2 mega ohms, and well, the voltage across the 2 mega ohms resistor, your input resistance, is basically your V1, right? And so if you just remember the voltage division for resistors in series, since this is so large compared to this one, Vs is more or less going to be equal to V1, okay, approximately equal to. There's going to be very little difference, very little voltage drop here. So Vs, so we have Vs equals V1, okay, or approximately equals V1. It's pretty accurate though. All right. So if these two are true, if we just combine these, what we have is we just combine these. So if we substitute for V1 here, what you get is V naught equals negative A V1, okay, and there's two ways to write that, but two ways to write this, but I'll before that, okay, what am I saying? Anyways, so we got this equation, but we need to be very careful. Let me just show you, like you might think we got this pretty easily. So if you have an open loop, if this is open, the calculation becomes pretty easy and everything's pretty simple and all. But I'll show you why this is pretty bad, and really it's pretty bad actually. So one thing is this equation right here. There's a very big assumption right here that we are actually operating in our linear region. It is true that the op-amp should, it's the intended purpose. We do want it to operate in the linear region. Otherwise, there's something wrong with our circuit. It's not operating according to our wishes. But so that's the assumption here. Okay, that's the assumption. And actually, I need to. What was the? Okay, wait. Let's see. I'm sorry for wasting time here. Okay, so the problem here is I just rewrote that equation. I don't know why I did this, but this is yeah, this is Vs. Okay, that's what I was planning to do. Anyways, so as I said, and I have no idea. Okay, so yeah, I marked it for that. Anyways, sorry for all that. So as I said, this is under the assumption that we are operating the linear region, and it still holds here. Okay, it's not like that assumption is gone. Okay, so what I'd like you to consider, one form of this equation is actually well actually before that I'll show you the reason why we might think this is good, okay, is that this gives us the gain pretty easily, so V naught by Vs is going to be equal to negative A, right? Okay, so this gives us the gain pretty easily, and it's a pretty large gain. So if you think about if you want a really large gain, this is a good thing to do. You might think like that. So you might so that might lead you to think that this is a pretty, this is a pretty useful sort of circuit, right? If we just keep this open, didn't even, if we don't just have this 20 kilo ohm resistor. But no, there are some issues here. There are some issues. As I said, this is under the assumption we're in the linear region. Same assumption here. If I just rearrange this a bit, if I just rearrange this equation a bit, what we get is Vs is equal to negative V naught by A. Now I want you to consider what the typical values for this are. Vs is for the op amps that we are going to be working with. This is typically, and well, as I said, this is the maximum range for this is the maximum range for V naught. It's limited by your power supply, right? It's limited by your power supply. Where is that diagram? Let's see here. It's limited by your power supply, and for the IC741, the op amp we're going to work with, this is in the range of 25 to 24 volts. So you need to see. You need to see that V naught is going to be in that range. Okay, that's it's going to be inside that range. And in this problem, and in general, op amps have a really large gain. So this was 2 times 10 to the 5. Okay, let's say that this is 16. Okay, let's say that this is 16. I just picked a random number in that range, 5 to 24. So this is a really small number, and this is the kind of like for these two values that we have. This is the maximum value of Vs. Okay, this is the maximum value of Vs. Well, if this is plus, anyways. So it's like this is the magnitude of this. This is basically limiting the range of Vs, and this is going to be a really narrow range. Okay, this is going to be a really narrow range. Okay, and there's no point. It's going to be really difficult in finding a cell. Okay, so this Vs was what? This was just our EMF over cell. It's going to be pretty difficult to find a cell with this small of an EMF, and even if you do, that kind of a circuit is not really going to have some kind of useful application. Okay, and the other thing that we thought that we might get a large gain here, again that's not true, because as I said, V naught is, well, it is a large gain, but for a very narrow and kind of useless range. And also we cannot go past our supply voltage, so it's not like we can get some large output or anything like that. So this circuit is actually pretty useless, to be honest. It's pretty useless actually. So not a good one. But in contrast to that, our closed loop circuit, if we just, instead of keeping this open, if we close this, okay, this is actually pretty interesting. First I'll talk about what's interesting about the result, and then I'll talk about what's interesting about what's the mechanism, what's happening here. So first thing, if I just rearrange this, I have V naught equals minus 2 V sub s. Now I want you to notice what this equation is saying. So we had our supply voltage, okay, that's Vs. Okay, so we just fit a cell here, okay, with an EMF of Vs, and due to this circuit which has this op amp, which has this op amp, okay, we are getting an output that's going to be equal to minus 2 times this, right? Minus 2 multiplied by this thing. Okay, so it should be pretty apparent that your op amp is actually doing an operation, right? It's taking this, you could say your supply signal, even, okay, your supply voltage, it's doing an operation on that. It's multiplying it by a constant which is minus 2, so reversing the polarity and multiplying the magnitude by 2. So this is an operation, right? This is performing an operation, and I talked about it in the last video a bit about why this is an operational, right, amplifier. That part came into the name. And here we see, actually, after doing a calculation, we're practically seeing why, how this is an operation. Okay, one sort of operation here. And the other thing to notice is, let's see what that is. Oh yeah, okay. And the other thing to notice, at least in terms of magnitude, you can see that this has been amplified, right? This has been amplified. This, uh, you know, your input, you could say input or supply signal was this, and the output, it's a magnified version of that. Okay, it's a magnified version of that, or an amplified version of that. Okay, so this has been amplified, okay, to give this, all right. So this has been amplified, and this is where the amplifier comes into the name. So I hope you can appreciate the naming of the op amp a bit more. All right, so that's what I wanted to explain about here. And this might be a bit of blabbering from me, but this is actually pretty useful, pretty useful circuit. Not just because we have this equation, but there's two more things. One is this gain, okay, this closed loop gain, what we are calling this, okay, is approximately -2, specifically this thing. It's not dependent on the open loop gain. Okay, it's not dependent on the open loop voltage gain. You can try to yourself redo the problem with any large value of a, okay, any large value of a, like this one. You're going to get more or less the same answer here. Okay, that's one thing. And the other is, unlike before, where our vs, the range of vs that we're allowed to use, or that we should use, is pointlessly narrow. This one is not. Suppose, say, I take the same limitations for v naught. Suppose, at most, which is the value of the power supply, or the maximum value of v naught, is 16, and I'm going to work with magnitudes because that's a plus minus thing here. So if that's 16, we have this is equal to 2 vs, and vs equals 8 volts. Basically what it means is that vs is going to be limited from negative 8 volts to 8 volts. Okay, if for a normal operation of the circuit or op amp. But this is a pretty good range. Okay, this is not a pointless range like the one before. Okay, so that's why this is a pretty good circuit. This is a pretty useful circuit. Okay, it amplifies my signal. It also reverses the polarity, and it we can use this for an appreciable range of supply signal, okay, or supply voltage. All right. I really don't want to extend this more than it has to, but okay, so have I discussed all that? I'll just pause for a bit. All right, we just have a bit more left. So, okay, so I've discussed all the good things about why this circuit is so great, and why this is so practical. Okay, it's very sensible. It's very practical. All right. Now I'm just going to talk a bit more about why the what's going on here is so great. Okay, or the mechanics here. Anyways, so what I'm talking about is, okay, first thing is clarifying that term is why this is closed loop voltage gain. Why we're calling this a closed loop voltage gain? Because this is not a very complicated reason. You have this is your output terminal, and this is your input. Okay, this is one of your inputs, and you have a feed. Okay, so you have a connection from your output to your input. Okay, you have a connection to your from your output to your input right here. Okay, right here. So um, this is actually called and well, before revealing the name, I'm going to show you, I'm going to tell why it's called like that. But anyway, so we have a connection here. Now let's just think about at the very initial stages of the circuit, what happens. So you have, let's go to here. Okay, this circuit. So this is VD. Okay, V sub D. There's going to be something. Okay, suppose, say, because of this loop, this has some value. Okay, and then this has some value, this has some value, and this causes you to have some kind of an output voltage. Okay, now what's going to happen is, okay, so you have a connection here. Okay, you have a connection here. You have this output voltage here. You're gonna have some voltage, and so here you're gonna have some current, right? Here you're gonna have some current. Doesn't matter, I drew the direction previously here, like this. I'm drawing it opposite here, but that doesn't matter. It's kind of like directions in KCL. It doesn't matter what which one you consider. as so long as you do the thing right. Anyway, so yeah, what I'm saying is there is going to be a current here either way, does either direction, it really doesn't matter. So there's going to be a current here, okay, from, okay, so this is pretty neat, and this is pretty important. I want you to pay attention here. There's going to be a current from this output, okay, from the output to the input, right, to the input, and this current is then going to influence the input, okay, and then you're gonna have your uh, vd is gonna be influenced by that, then that's going to influence the output, and then that's going to and then that's going to influence the input. So it's like a feedback, right? It's a feedback cycle, right? The output is it feeds back into the input, right? Your output, and let me write that. That's actually a pretty neat thing I just said. Well, I'm not boasting about myself or anything, but yeah, that's a pretty good way to put it. I think the output feeds back into the input, feeds back, okay, feeds back into into the input, okay, into the input. All right. So, and this is the part that we care about, this feeds back part, okay. So feeds back, okay, the output feeds back into the input. That's why this mechanism is called feedback, okay. This mechanism is called a feedback. And this loop right here, mainly this one, okay, this one right here, okay, this is called a feedback loop, okay. This is called a feedback loop. I think the naming is pretty obvious. So this is called a feedback loop. This is called a feedback loop. Oops. All right. And yeah, I think I personally think this is pretty neat. So just because you're allowing the output to feed back into the input, you're getting such a practical and useful circuit. So I think that's pretty neat. And one last thing that might be on your mind, and it's really good if this thing is in your mind, if you are thinking about that, if you are mulling about this a lot, is that okay? So I said that there's kind of like a feeding back cycle. Then why is this ratio constant? Why is this ratio constant? And overall, why is everything kind of like steady? Okay, why is everything kind of like steady? Shouldn't I have some sort of fluctuation? And you would be right. You would theoretically have some fluctuation at when you just start the circuit. Okay, if suppose there was some switch to start the circuit, you would have some fluctuation at the beginning. Okay, um, let me draw a graph right here. um, let's see. So axis here, it's mainly on the negative part because we got the ratio as negative. um, so this is v naught. This is basically the v naught axis. Well, I'll write it. On top anyways. I'll write it on top anyways. This is the negative part. um, this is your origin, this is your vs. So this is clearly, you just have a straight horizontal line at the bottom, and this is basically what you'll see. So you have whoops whoops um, let's see. I'm kind of like losing a habit of this because of using the writing pad. But anyways, so um, this is what our equation tells us that our you know our graph should look like if we draw this graph. So I might think, okay, so where is all that thing about feeding back, and kind of like if you think about, there should be a slight fluctuation. Where's all of that? Where's all of that? And well, it is there theoretically. You do have some fluctuation at the beginning. uh, it's your input voltage should kind of wriggle around like this a bit before, okay, initially, and then it becomes stable like this. So you reach equilibrium, or in electronics we call this steady state. So this is a steady state, and that's a transient. But so this is a steady state. So you have some fluctuation in the beginning, but to be honest, I don't believe, or I don't think this is of some uh, this is of some practical this is something to consider practically, because it's not because it's not because we just get our result at the end. It's because this time period is actually really short, and by really short is what I mean by that is I actually tried simulating this circuit in Spice, okay, and I kept going smaller and smaller. I even went I considered the full time interval, okay, for the graph to I think even 10 picoseconds or maybe even 1 picosecond, okay, and you can imagine what the smallest unit was if the whole axis was up to just 10 picoseconds, okay, and even I took a very small unit step, as small as possible, okay, and I still didn't notice this initial fluctuation. So it takes that little time for the circuit to actually reach steady state. That's why this is not really something that important, but I still find it neat. I still find it neat, and the whole feedback process, I think, even though it reaches steady state and it's like your circuit is more or less your normal, at least how we're considering, it's more or less your uh, normal circuit with one cell and one VCVS. Doesn't look that different from that, but I still think all of this mechanism and everything is pretty neat, and the result really just speaks for itself. We got something that I don't think we got before from any other device, an amplification, and even an amplification, a reversal of polarity. It's pretty neat, right? So that's the end of what all that I had to say. I'm pretty sure a lot of what I've said is probably not, you won't need it in class or anything, but I just wanted to show you just how great op amps are, to be honest. It's one of it is my favorite circuit element, I'd say. So with that, I'll end this video and study smart.